path connectedness, and this is the last thing that we're going to say about connectedness. Maybe we'll finish today, I'm not sure. But path connectedness. This is something I alluded to last time, and I think actually we gave a definition, basic definitions at the beginning or at the end last time. Path connectedness is another kind of connectedness that's not about, the ordinary. If you just say connected, that means that there is no separation into two sets, U union V with certain properties. But path connected is something different. I will recall, I think I wrote these basic definitions at the end last time. A path from X to Y is a function, a continuous function f that goes from the closed interval to X with f of 0 equals X and f of 1 equals Y. So the way to think of this is, here's my 2 points. A path from X to Y is, you should think of a path as being, something like this. A little route, a little map, a little line drawn on the ground that goes from X to Y. But actually, the line itself is not how we define the path. We say that the path is just a function from the standard closed interval 0 to 1 to X. And so this line that I'm drawing over here, really more technically, that line is not exactly the path. That line is the image of f of 0 to 1. Like when you plug the interval into f as a function, it gives you this set over here. You could say this set here is the path, but actually we will see later on, it's much more convenient to think about the path purely abstractly as the path is that function. All right, that's what a path is. And then we say a space is path connected if any 2 points in that space have a path between them, which that would be true of this set over here. So a space X is called path connected. Actually, this we could just say for any set. Can I say instead of space? With connectedness, there's a bit of a distinction between the whole space being connected versus a subspace being connected. But in terms of path connected, it's a little bit simpler. A set X is called path connected when, anybody remember what I said last time? The idea is still more or less like connectedness, where it's all sort of in one piece. But phrased in terms of paths, like this one right here is path connected because, do you remember? Something about paths. Path.
For any 2 points, there exists a path.
Yeah, for any 2 points in there, there's a path from the one to the other. So a set is path connected when I will say for all x and y in X, there exists a path from X to Y. That's what it means to be path connected. For all points X and Y in the space, there exists a path from X to Y. All right. So what are some examples of, what I want to talk about today is for sort of what's the difference between path connected and connected, like ordinary connected, and then are there similar properties for path connected as there are for connected things? The answer is yes, there are similar properties, and we'll talk about one or two of them. Examples of things which are path connected, so something like Rn is path connected. In fact, in Rn, you can take any 2 points in Rn and connect them by a straight line. That makes a path from one point to another. So Rn is connected, it's also connected, but it is path connected. I'm going to write sort of a list here. How about intervals in R. Intervals in R are path connected because if you have an interval of points in R, you can always get from one to the other along a path, which would just be the straight line in R from one to the other. Intervals in R, other things like balls in Rn. I mean, at least the standard Euclidean balls, like the ones that actually look like circles or whatever, discs and balls in Rn. Also, what else? A single point counts as path connected. A single point. If your set consists just of one point, is it true that that one point has a path to itself? Yes, you can use the path, which is a constant function. Remember, the path technically is a function, and this function, if it's a constant function, then it makes a path from one point to itself. All right, all of these are all path connected. All right. What is not path connected? I mean, I can give you an example. Something like in R here, if I had this interval here union with this interval here, say a set which has, maybe this is 1, 2, 3, 4. So that's what I'm drawing here is the open interval 1 to 2 union the open interval 3 to 4. This is not path connected. Since you have to say specifically, not path connected would mean you can find 2 points in that set where there's no path from one to the other. Anyone want to tell me what's 2 points in here where you can't get there from here? That's what you want to think about. There's no path from one to the other that's inside the set. This is not a trick question. I'm going to fill in the blanks. And cannot be joined by a path inside that set. What I mean. 2 and 3, yes. Although I wanted this, I wrote those as open intervals. So 2 and 3 actually don't count as part of this set. Can you give me a slight variation? Sure. Yeah, these are kind of ugly numbers. I mean, not your fault, my fault. Yeah, 1.5 and 3.5 are, here and here, right? And those 2 points cannot be joined by a path which lies inside that set. Okay? Great. So that's what it looks like to be not path connected. Now, that set is also not connected. So you should immediately be wondering, like, isn't this just the same as connected? But it's not. And I gave you one example of this a few times ago, which is a very weird example. But here's an example of something which is connected but not path connected. It's this thing. Remember that thing? This is, in detail, this would be 0 cross minus 1, 1. That's this vertical part. And then this curvy part is the graph of sine of 1 over x along some certain range. I mean, I just made it stop here, but it doesn't really matter. All right. Those two things, I mean, they look like two different pieces. And it is true that this curve part never actually reaches the line because it oscillates up and down infinitely often before reaching the y-axis. And so this is an example where it is connected. This is connected. There's a name for this. This is called the topologist's sine curve because topologists like this. The topologists. Is it that way or this way? Maybe that way. I don't know. Sine curve. Because topologists think that this is interesting. It is interesting from the point of view of topology. It's not terribly interesting in other contexts. But this is called the topologist sine curve. And it is connected. This is what's interesting about it. It is connected. You cannot separate it using two open sets like a U and a V. Because, for instance, if you wanted to wrap an open set around this vertical part, your open set automatically would have to be like a little worm in R2, and it would have to catch some of the curvy part. So you cannot separate using open sets the vertical part from the curvy part. So that's why it is connected, but not path connected. Because you cannot go, say, from this end to a point on the vertical part along a path. Because a path has to have sort of a finite length, and this thing you have to go through like an infinite amount of length before you get to the vertical part. All right, so this is not path connected. This is everybody's favorite example. If you approach a topologist on the street and say, give me an example that's connected but not path connected, this is what everybody will say. There was another example that's given in our book, which I actually have not heard this word for it, but this is called, here's another one, the topologist's spiral, I think. Oh, they have a flowery, the topologist's whirlpool. And this is meant to be similar, where you have one piece which is kind of like the edge, and then the other piece which like infinitely closely approaches it. And it looks like this is in R2. It has the outer edge, I'll draw in blue, is a circle. I'll make it nice and round. That's not, there we go. I'll try and put the center there. All right, that's like the outer edge, and then you have another thing which is approaching that, but sort of it takes forever to actually arrive, and that is a spiral like this, which it's a spiral with increasing radius. It goes out, but the radius doesn't go out forever. It just approaches 1. So the blue part has radius 1. All right. So what this is really, it's just S1 is the blue part, the unit circle in R2, union with what I drew as the red part. You can actually describe fairly easily. This is in polar coordinates. You can write it this way: theta over theta plus 1, comma theta. So this is polar coordinates. So the theta here, you just increase the theta forever. That makes it just keep going around forever in a circle. And then this is the radius coordinate in polar coordinates. And you will notice if the theta, first of all, this is a fraction which will always be slightly less than 1 because the numerator is less than the denominator. And as theta goes to infinity, though, this radius approaches 1. So that's why it makes a spiral that looks like this. It's a spiral of radius less than 1. Actually, it starts off having radius 0 when theta is 0. And then its radius increases towards 1. It approaches 1. So that's why it looks like that. All right, this is called, our book calls this the topologist's whirlpool. And it has a similar property. It is connected, but not path connected. So it's connected because you can't make a neighborhood around the blue part which excludes all of the red part. I mean, as an R2 neighborhood, you can't do it. But it is not path connected because you cannot, on a path, say, make it from the origin all the way to the blue part. There's no path that can go from there to there because that would require sort of an infinite path to get there. All right, so this, again, is connected but not path connected. All right. I would say in general, the concept is not this idea of being path connected but not path connected. This is something that, to my knowledge, doesn't really occur in reality. Like people in real life care about connectedness when they're talking about, like, am I gonna get electrocuted by this electrical wire? The answer is it will if it gets connected to you. You don't have to worry about things like this in the real world because these examples typically involve some kind of an infinitely long thing which approaches asymptotically some other thing, and that doesn't exactly happen in real life. So sort of, I would say in real life, connected and path connected are kind of the same thing. But in abstract spaces like this, there can be differences. All right. Let's talk about, okay, so it is possible a space, come on. A space can be connected but not path connected. Connected but not path connected. All right. They really are two different concepts. Could it be the other way around? Could it be path connected but not connected? Let's think about that. Can it be path connected but not connected? All right. Not connected, but path connected. So what that would look like, not connected means that the set basically looks like this in two pieces. It has a U and a V, right? Can something that looks like that also be path connected? Well, I would say if it looks like that in two pieces, I can choose one point over here and one point over here. Kind of seems to me like there can't be a path from one to the other. Now this shouldn't be totally convincing because maybe there's some ridiculous wild example where this actually happens. But I would say my gut instinct would be that is sort of not possible. I feel like there can't be a path from X to Y in an example like this. In fact, could I say even more specifically? It seems to me if U and V make a separation of the whole thing, then those same U and V should separate the path, right? But an ordinary path should not be able, you can't separate a path because it looks like an interval. So this is my idea. I feel like this is impossible. I want to do the actual proof of this, but it's basically what I said. There's not all that much details that goes into it. This is impossible. I would say my basic idea, since the separation, X equals U union V would also separate the path from X to Y. But I feel like that should not be possible because a path is basically like an interval, and an interval cannot be separated, all right? This is my vague idea. I want to actually talk about some details for this. So I'm going to write this as a theorem. It says if X is disconnected, that is not connected, then X is also not path connected. All right. If X is disconnected, then X is not path connected. So let's see if we can, I'm going to try to make formal what I said up here. If we assume X is disconnected, so I'm going to say let X be U union V. This is a separation. All right, and then we're going to somehow use that to demonstrate that X is not path connected. And I'm going to try to make this setup exactly like I did in the picture up here. Maybe I'll just copy my picture down here. No, I lost it. All right, so I'm going to, just to get us started talking about paths, I'm going to say take X in, well, actually this is going to be easy if I do. You can tell. I want to do this by contradiction, right? I want to take X over here and Y over here and assume that there is some kind of path and then show why that's actually not possible. So I'm going to say to get a contradiction, let's assume that X is path connected. All right. And that means I can take X in U and Y in V This is possible because U and V are not both empty. Actually, neither of U and V can be empty, right? U and V are both not empty. That's what I meant to say. Because they make a separation. The sets in a separation cannot be empty. So take one point on the one side, another point on the other side, and then because I assumed X is path connected, then there exists a path, which I will call F, 0 to 1, to X, from X to Y. All right. And we're going to try to say why this makes a contradiction. All right. Remember, like I was saying before, like this little line here is not the true path. The path is a function from 0, 1 to X. This line here, if you want to say what it is, that line as a set is F of the closed interval 0 to 1. That's what that line is. And what I want to say is this separation of U and V, they actually would make that set also separated according to U and V. So what I'm going to say is then now it's not exactly U and V that I want to talk about. It's separating that interval. I will say F of 0, 1 will be separated by U intersect F of 0, 1 and V intersect F of 0, 1. That would be like this part of it. That's U intersect the path, and then that part of it. That's V intersect the path. And apparently there's just, I drew it as if it was sort of going through here, but apparently there just isn't anything else going through here. That's because the entire space is already separated into U and V. So these points, they don't actually exist. All right. Then this will be separated by those, and that means, so, F of the set 0, 1 is disconnected. And what's wrong with that? This is supposed to be a path. And I was saying before, like that seems not possible because a path is supposed to be something that looks like a closed interval. F of 0, 1 is disconnected. Can anybody say why? How do you know this is impossible? This is actually a contradiction. Although maybe it's not obvious the precisely what's wrong with that. This is a contradiction. Since this is actually something that we talked about quite a few times ago. Perhaps you've forgotten by now, but it was one of the first theorems that we had about connected sets and functions. And it says, if a set is connected and you look at the continuous, if you have a continuous function, then F of a connected set is also a connected set. If you plug a connected set into a continuous function, then what you get out is also connected. And that actually is where the contradiction is. We said that this is disconnected, but that thing is connected. It's a closed interval in R, is connected, and we plugged it into a continuous function. And that means this thing has to be connected. So that's the contradiction. So this is a contradiction since, I will say, 0, 1 is connected, and F is continuous. So F of 0, 1 is connected. And that's our contradiction, right? This and this are in contradiction with one another. So this is an important fact, and we're actually going to talk a little bit more about this. But I hope you all remember, if you have a connected domain and you plug it into a continuous function, then the range is also connected. That's what I've been referring to as the intermediate value theorem. That's basically the same as the intermediate value theorem if you're talking about calculus. All right. The end. Okay. All of this demonstrates that if X is disconnected, then X is also For some reason, we don't say path disconnected or dispath connected. We just say not path connected because it's a little weird to say. Dispath connected. All right? Disconnected implies not path connected. So this I could write like this. Disconnected, can I just say, for now, not connected implies not path connected, right? That's what we just demonstrated. This actually looks more convenient if you read it as the contrapositive. Not connected implies not path connected. The contrapositive of that, you negate both sides and swap them around. That would say path connected implies connected. That's a nicer looking theorem. It's just the contrapositive of that, but it says if X is path connected, then X is connected. So you could say path connectedness is somehow stronger than ordinary connectedness. Anything that's path connected is automatically connected, but the other way around is not true. There can be things that are connected but not path connected. The topologist sine curve is your favorite example. All right, if X is path connected, then X is connected. All right, excellent. This is the fundamental sort of thing that you could say about the relationship between path connected and connected. If it's path connected, then it is connected, but the other way around is not necessarily true. There are, now I don't want to go through like everything that we've talked about connectedness, but you can take any theorem you've ever heard of about connectedness and try to do the same thing for path connected. So I will just say most theorems about connected are also true of path connected. And I don't want to go through all of them, but like for example, this is a true fact. If C1 and C2 are path connected and C1 intersects C2 is not empty, then C1 union C2 is path connected. This is, we had the same theorem for connecteds. It's also true for path connecteds. And this, if you wanted to prove this, actually I think this is going to be on the homework. But to demonstrate this actually requires a totally different arguments from the ordinary connectedness version of this, because it's all about paths rather than separations. But yeah, that's still true. And there were others, something about the product of path connecteds is path connected. That's also true. And so on. Most of the stuff that we've said about connected sets, the same kinds of things are true about path connected sets. There is one, and what I would consider like the most important one, I actually would like to talk about the details. And that is just this thing about continuous functions. So I would like to do just this one example. If X is path connected and F X to Y is continuous, then F of X, the range or the image of X, is path connected. All right, so the exact same theorem we did for connected, I want to try to do this for path connected. All right. The details of this are actually fairly straightforward, I would say. I don't know. Maybe I always say that. I hope that you would feel this way. Can we try and get this going ourselves here? We have to show that f of the big X is path connected. So perhaps starting there. Someone want to suggest how we should get started? I'm going to start by saying sort of what it is that we have to show here. How would you demonstrate something is path connected? Anybody recall the definition of path connected? Yeah?
Would you just show
All right.
that like any two, like f of like little x and f of little y
Yeah. Path connected means any 2 points in there, there's a path from one to the other. So I'm going to start by saying choose 2 points in here. Now, you could call them A and B or X and Y, but since there are 2 points in f of big X, I can choose them to be, like she said, f of little x and f of little y. So I'm going to say, let's choose, maybe I'll call them A and B just so I don't confuse them with the big X and the big Y. F of A and f of B in f of X. So that means A and B are in the domain, right? I'm choosing 2 points in that set, f of X, which I'm trying to show is path connected, and then we'll find a path from f of A to f of B. That is, it has to be a continuous function. I.e., maybe I'll just spell that out. What would that look like? It would look like, usually I call a path f, but not this time, I guess, because I have something else called f. I'll call it, how about P? P for path goes from the interval 0 to 1 to y with P of 0 equals f of A, P of 1 equals f of B. That's what a path from f of A to f of B means. All right. Okay, maybe I'll try and draw a picture here just to get us going next. So what we have is, our function goes from x to y, and I have chosen 2 points, f of A and f of B, and f of B here. And those two, they come from 2 points over here, A and B, right? And what we are trying to do is we are trying to find a path from here to here. This is sort of what we're looking for, right? That's what I called P, is that path. We're trying to find a path over there. And what we know, like what we have to work with is, first of all, f is a continuous function, and we have also assumed that x is path connected, all right? Anybody want to suggest? How can we use one or the other of those assumptions? F is continuous and x is path connected. I think one of those is useful by looking at the picture. You can realize something or other from one of those things. What do you think? Either using the fact that f is continuous or that x is path connected. You can say something interesting about our setup here. What do you think?
I'm not sure, but there exists a path between A and B.
Yeah, since x is path connected, there is a path from A to B. Okay. Like that. Maybe I'll call this one Q. I don't know. I'm running out of good letters here, but I will say since x is path connected, there exists a path Q from A to B. What that means is, Q of 0 equals A and Q of 1 equals B, right? That's what it means to be a path from A to B. Okay. Our goal is to create a path over here. Anybody got a brilliant idea? How could you take this path and somehow turn it into this path over here? Knowing that there is a path over there, can we somehow do something to it to create this path over here? You got an idea? Yeah, how about just plug this path into this function, all right? Then what will happen, like this first endpoint A ends up at f of A, the last endpoint B ends up at f of B, and then everything in between, I guess, makes a path in between, all right? So that actually is the definition of P. So I'm gonna say let P equal, she said f of Q, yeah. it's like this, f composed with q. It has to be a function, remember? All right, this is now a function. In order to be a path, it has to be a continuous function. Are you sure that that's continuous? The answer is yes, because we assumed f is continuous as part of the theorem, and then q is continuous because q is a path. So this is continuous, since f and q are continuous. Right? And is it really a path from f of a to f of b? You have to check the endpoints. What is p of 0 and what is p of 1? You know, if this is going to work on our picture, we need p of 0 to be f of a and p of 1 to be f of b. But we can just plug this into definitions. This would be f of q of 0, because that's what p is. And then I believe I said already, you can see it at the top there, q of 0 is a. So that is f of a. And this one, p of 1, it would be f of q of 1, and q of 1 is b, so this is f of b. So p is a path from f of a to f of b, and that's it. Right? That's what we wanted to find, was a path from f of a to f of b. So it all works out nicely. All right. So this has been a demonstration that if you have a continuous function, and a continuous function takes a path-connected thing to another path-connected thing. That's the moral of the story. All right. Like I said, there are many other theorems that we could talk about for path-connecteds, but I've had enough with the connected and path-connected. All right. Any questions about that? One last thing that I want to discuss is, and I'm just not talking about the details, but just to, there may be some homework problems that mention this. We can also discuss what we call path components. Path components is like if it's disconnected, or if it's not path connected, you can break it up into a bunch of path components. Like, for instance, if I just have sort of two blobbity blobs like this, this has two path components, right? The one on the left and the one on the right, and they are different components because you can't get from a point on the left to a point on the right along a path. All right, so that one has two path components. I will say it also has two sort of ordinary components, although that means something different. Path components means the points over here cannot be joined by a path to the points over here, whereas when I say those are two different components, it means there's a separation that separates one from the other. Those other weird examples, though, like the topologist sine curve, this thing, this one is connected, which means it only has one component. But it has two path components, because in terms of paths, it is actually not connected anymore. It has two pieces, the vertical piece on the left and the curvy piece on the right. So this has one component, if you're just talking about connectedness, but two path components. All right, and they would be the vertical part is one component, one path component, and the curve is the other path component. All right, so there is, you can say, and then you can say a lot of sort of theorems about path components versus components, which, again, I don't really want to get into, but you may be encouraged to think about this on your homework. All right. Any questions about that? Excellent. This, I believe, is all there is to say about connectedness, at least for our purposes. Any last thoughts about connectedness? It's interesting, in my opinion. connectedness and path connectedness. All right, you'll have some practice with those on the homework. Our last, I said that the rest of the, I said after spring break, the rest of the class was kind of about the two C's, connectedness, and the other one was compactness. So maybe in our remaining 10 minutes, I can remind you about compactness. This is something you talked about in real analysis, but perhaps forgot about by now, or maybe never felt good about in the first place. We can talk about it. I'll refresh your memory this time around. Compactness. A set can be compact. My very intuitive notion of compact is it's a lot like closed, but a compact set is not allowed to be infinite. It has to be, well, in real analysis, you all learned the Heine-Borel theorem, which I hope you remember, means a set in R, a subset of R is compact if and only if it is closed and bounded. And that's a fairly easy thing to think about. A compact set is basically like a closed interval. It's not that's bounded. It's not allowed to stretch out to infinity. That's not compact. I think that's why the word compact comes from, is like it can't go out to infinity. But it also has to be closed. Anyway, that was something that you talked about in real analysis. Actually, the definition, so from real analysis, the definition was this, and this actually, I'm going to write it, but actually we're not going to use this in this class. We say X is compact if and only if. I didn't remember this definition. It has something to do with sequences. You actually remember?
Does it mean it has a sequence that has a convergent subsequence that converges to something that's also in?
Yeah, right. It means every sequence in X, congratulations for remembering that. You get no bonus for it, but I'm impressed. Every sequence, this is the kind of thing that you remember until the end of your real analysis class, and then you remember it again for like a week when you take the comprehensive exam, and then you don't remember it after that. Every sequence in X has a convergent subsequence, and that subsequence converges to something in X. A convergent subsequence, and I will say its limit without the apostrophe is in X. That's what the definition from analysis of compactness typically looks like that. This, for our purposes, is not very convenient in a topological setting because, you may have noticed by now, we don't really like to talk about sequences and limits of sequences. That is a very nice thing to talk about in real analysis. It's not so nice in topological spaces. I would say one big reason is that in any topological space, we saw examples long ago that sometimes a sequence can converge to more than one value. In a non-Hausdorff space, this can happen. Like I believe we talked about examples in the finite complement topology on R, where a sequence can converge to all numbers at the same time, which is totally weird. So sequences are not generally the way that we make definitions in topology, because sequences are kind of weird in some topological spaces. All right, but as I said before, you all learned the Heine-Borel theorem. The Heine-Borel theorem, it says that that thing, what I said there about sequences, is equivalent. X is compact if and only if X is closed and bounded. That, to me, is a much easier way of thinking about things, even in real analysis. I would rather think of the set in these terms than in terms of imagining all sequences and trying to find convergent subsequences. But unfortunately, this also is not really appropriate for discussion in topology in general. I don't know if you thought I was going to like this better. I do like this word just fine. Closed is something we talk about all the time. I personally like talking about open more, but closed is fine. It means the complement is open. What about bounded? This actually, I have problems with this when I try to talk about this in topology. Bounded really is something that only makes sense in Rn, really. Bounded means the whole set can fit inside of a box or something like that. Really, boundedness makes sense in a metric space if you have some kind of distance. But there is no good way to talk about bounded sets in something that's not a metric space, like in something like the finite complement topology or whatever. That's not a thing. Bounded is not. It's not a strictly topological notion. This basically requires a metric space, which is fine, but I want to try to do this in pure topological spaces without assuming that there is a metric, all right? So this also is not how I want to talk about compactness. Topologists, when they talk about compactness, they use neither one of these definitions. Anybody remember? There was one other thing that you talked about in your real analysis class, which probably you thought was the worst out of all three. There was another way of thinking about compactness. Anybody remember the other one? You may recall, you may have blacked it out because it was, in my opinion, in the context of real analysis, weirder than these other two ways of thinking about compactness. Our definition, which you did talk about in your analysis class, you probably tried to avoid it and use closed and bounded instead. Here's the definition that we're going to use. This makes complete sense in topology. You don't have to play any games with sequences or boundedness or anything. X is compact. Maybe this will jog your memory. When every open cover has a finite subcover. You remember that thing? Every open cover has a finite subcover of X, I should say in there. Every open cover of X has a finite subcover. This was another formulation of compactness that I'm sure you saw at least briefly in your analysis class. So in our remaining 3 minutes, maybe I can just refresh your memory about what this means. Open cover and finite subcover. This probably seemed very weird to you in your analysis class, although maybe now that you're a seasoned topologist, maybe this doesn't seem so weird. An open cover is just some kind of description of a bunch of open sets that cover up the whole set that you're talking about. So an open cover is a collection of open sets. Maybe I'll call them like U alpha, where X is a subset, or X equals the union of the U alphas, where alpha could be any kind of index set. It doesn't have to be finitely many sets. It could be infinitely many. It could be uncountably many if you want it to. An open cover is a collection of open sets where they cover up the whole thing. If you take the union of all of these, you get the whole thing. I typically would imagine these as being like little patches. They're individually open sets, and you can sort of cover up the whole thing by using these little patches. For example, any basis of a topological space is an open cover because every point in the space can be covered up with a little ball or something. All right, that's what an open cover is. And a subcover just means you only take finitely many of them. Well, a finite subcover means you only consider finitely many. So a subcover is just, some but not all of the U alphas, which still makes a cover, or still covers X, big X. All right. And I will give you one example of a non-compact set using this open cover business. So let's talk about, we're going to do a lot more details, but we only have 1 more minute here. Let's say let X be, this is an example that you saw in your analysis class. This is a recurring example in real analysis. You talk about this particular example all the time, although I don't know if you miss it. So this set does not include 0. It does include 1, a half, a third, a fourth. It includes all the fractions 1 over n, but not 0, all right? It turns out that is not compact, and I can describe for you an open cover with no finite subcover. Here's an open cover. I'm going to say let u, I'll call it un, be the open interval 1 over n to, how about, well, I could use infinity and then intersect with x. So these are open intervals. I don't really need the intersect with x. Let's leave that out. That's technicality I don't really care about at this point. Can I just convince you that this has no finite subcover? What these look like, these are sort of intervals. They always go out forever. The first one goes 1 to infinity. The next one goes 1/2 to infinity. The next one goes 1/3 to infinity, 1/4 to infinity, etc. Right? Now, here's 0. Is it true that these things actually cover up all of x? I believe it is true. Every one of those red dots eventually is actually part of one of these open intervals. And so that means all points of x are covered by these intervals. But if I only use finitely many of these, it no longer covers all of x. If I stop at some point, then I will necessarily be missing some of the red dots. So that's why x is not compact. This is an open cover, but this has no finite subcover. Because it don't, right? If you only use finitely many of them, then that means you're going to miss some of the points that are really close to 0. All right, much more about covers and subcovers next time. And I will grade your tests tomorrow. Sorry it's taken me so long. And we will also have homework to look at over the weekend, so check